specific errors on that. So now the question arises, well, we'd like to be able to calculate posterior probabilities for hidden states and for hidden state paths. So the question is, how do we do that? I think based upon what we were just talking about a moment ago, you can probably get a bit of a glimmer about the direction we should go to try to get at this posterior probability. What basic direction might we try to apply to start getting at these posterior probabilities? Yeah, I mean, the basic words apply here. So, you know, we want to get a posterior probability, and Bayes is kind of our standard way of doing that. So now we start to think about, okay, well, how might we do that? So let's try to write some Bayes law for this. So we just said we wanted something like that, right? So from a Bayesian point of view, I mean, just trying to basically plug this into Bayes' law, what ingredients would go to help us get this? Right. So we're going to have a likelihood. So you're basically telling me to put the observation first. What else? Yep, we can have a prior. What else? Sorry? Yeah, so you're telling me to average this down here. Basically the same thing. So just to be completely explicit about this, one very, very simple way of writing this, in some ways it's even simpler, just to kind of keep in mind what we're doing here, is that this denominator really is just that, right? So we're basically summing the probability of the observations over all possible paths. That's the challenge that we face when we want to compute posterior probabilities. Because as we just saw, there are a lot of possible paths. We are not going to exhaustively enumerate them. So the question is, does the Markov chain give us any magic for being able to compute this summation over all possible paths that's indicated here without effectively doing exhaustive enumeration? So what do you think? Okay, and elaborate. What makes you feel that?
So it's the average likelihood of time. So if we know, like I'm just guessing here, but if we know the like pi or whatever, like
the stationary distribution.
Yeah, stationary distribution for every state, then you might be able to.
Well, okay, that's an interesting direction. The thing that's going to interfere with that is our unique sequence of observations. So stationary distribution is sort of like calculating, as you were getting at, like a statistical average over some kind of infinite process that's just kind of converging to statistical averages. Here we're really trying to compute something for a very specific, you know, I mean, the casino, we see a particular set of dice rolls, so that kind of interferes with just trying to get the statistical average. So I think, if we go back to the kind of computational complexity problems that we did for our basic model building problems, where we would try to say, okay, let's draw the information graph, let's try to factor it, let's try to see, does this factor? When you hear questions about computational complexity, go back to that kind of picture, because basically that will very quickly get at whether you have a pathway in your factoring of the joint probability that can get you a kind of a dimensional reduction and improve computational complexity. So maybe one simple way we could start to do that would be to draw a picture. So, what kind of picture might we draw here? Sure, yeah, we can draw an information graph. So, I'll just focus in on one particular variable, let's say theta t, and let's build up our information graph around that. So we've got, let's say we've got an observation, x sub t, that depends on it. It itself depended upon a previous variable t minus 1, clear, which itself had an observation associated with it. And for completeness sake, I'll also include, next variable t plus 1, and its associated observation. Okay, so we've got kind of the basic skeleton there, right? Okay, so this is a picture of the joint probability equation, right? It shows us basically what the factors that get multiplied to make the total joint probability. When I try to think about computational complexity on structures like this, and in particular inductions, which are basically the key to algorithms, I like to use this kind of a picture in the following way that I'm going to show you. So basically, when I look at this probability of x, which explicitly is this summed over all possible theta paths, I basically think to myself, well, that's got theta 1 in it, it's got theta 2 in it, it's got theta 3, all the way on up to theta n, across the whole time sequence theta. That's a difficulty. And then I've also got this theta t that I'm going to zero in on for trying to break this process down. So I can see in my diagram that it's only coupled to the previous variable theta t minus 1 and to the following variable theta t plus 1. So one way that I could solve this is if I could get an induction that would allow me to compute probability up to theta t based only upon the previous theta t minus 1, which is sort of analogous to Viterbi, right? So let's try to do that. One basic way of picturing that is I'm going to divide my information graph basically to indicate what it is that I want to include in my computation. So maybe I'll switch colors here. Let's say that what I want to compute is the probability up to theta t. So I'll just draw a little line here saying I'm not going to compute anything after theta t. So then I'd like to compute that probability based upon the exact same thing but one step over. So I'll do the same thing over here. I'll just draw the same line one step over. Okay? All right. Doesn't look like I've achieved anything here, does it? Just drew a couple of lines. Now I'm going to start labeling parts. So notation is your friend here. So this whole domain, everything to the left of this line, is, I'll call it P of theta t minus 1 vector, comma, x t minus 1 vector. And just for completeness sake, I'll also note that the whole domain up to the second line is, of course, p theta t vector x t vector. Okay. So now let's say I want to get p theta t x t from the previous p theta t minus 1 x t minus 1. What's left? Well, the only things that are different between them, everything else is shared, is just those two edges. So immediately I have an expression. I can just write down, well, what's that? That's the transition. What's that? That's the emission, right? So I can write down that is p of x t given theta t, and that transition right there, I'll just write where I've got a little bit more space here, p theta t given theta t minus 1. Basically is that edge right there. Okay? I got an equation. So my recursion, my induction, is just p theta t comma x t equal p theta t minus 1 x t minus 1. My transition and my emission. And I will shift that up so that hopefully you can read it. Okay, so I've got an equation that gives me what I want to find in terms of the exact same thing at the previous step. And following the exact same process as Viterbi, can I get this for t equals 1? Yeah, for t equals 1, that's trivial, right? It's basically I can more or less instantly write down p theta 1 comma x1, and then from that I can get p theta up to theta 2 up to x2 and so on and so forth by this equation. Okay, so this, you'll notice I can compute, if I have p I'll write it this way, but just bear in mind that's only a single variable, so it's pretty much trivial. If I get this, then I can get this, and so forth, all the way on up to the end. Right? So, so the first good thing to notice is that this last thing that we just got, what is that? That's the numerator of the posterior probability that we were trying to calculate. So we're halfway done. Actually, we're more than halfway done because the last part is trivial. We can actually get the denominator as well. So the next thing that I want to do here is let's say I want to get rid of in this step right here, let's say instead of calculating probability theta all the way up from theta 1 up to theta t, I just want to get probability of theta t, that specific variable, to be in some state. Okay? That's analogous to the previous problem that we talked about, where in the first part we talked about the probability of the entire path, and in the second part we talked about the probability of just some specific point on the path, in other words, some specific hidden variable. Well, we can make a very minor modification, and we can get that too. So, what do I want? I want theta t to be in some specific state. Shall I make explicit what state I'm talking about? Sure. So I'll write theta t to be in some state S sub I. And then our complete observation sequence up to xt. Now, I can follow the same basic logic here. Let's just write down the exact same thing here, one step to the previous time step. So I'll write that equal to p of theta t minus 1 to be in some state, let's say S sub j, comma, x t minus 1. And again, I'm going to have to write my transition. To save space here, I'm going to omit the S sub i's and S sub j's here. I'm just going to write theta t given theta t minus 1, and I'm going to write x t given theta t. Okay. So, there's only one problem with this expression. Here we have just theta t, right? Here we have theta t and we have theta t minus 1. We want to get rid of theta t minus 1. How can we do that? Yeah, it's just sum over all possible values of theta t minus 1. So basically that means all possible values of j in this nomenclature, okay? So now what I have is a version of this recursion that allows me to get the probability for a specific state and the entire observation sequence. So one way of saying this is I'm summing over paths now, right? By the time I get to state theta t, what portion of path space have I summed over? Well, can you give me some kind of description of what set of paths are going to be included in this probability? Well, we're definitely summing over theta t minus 1, but you'll notice that by this definition, we would get this piece by the exact same equation, right? Because it's just the same form as on our left-hand side. So we would get it by summing over theta t minus 2, which we would get by summing over theta t minus 3, and so on. So this is called forward probability summation. What it gives you is basically from p theta 1 comma x1, which is trivial to get, we can now compute probability theta 2 comma x 2 vector from which we get p theta 3 comma x3 vector on all the way up to p theta n comma xn vector. Now what's the relationship between this last thing that we just got and our original Bayes law that we wanted to compute? Well, it's almost exactly the same as our denominator. So we're actually almost done here. All we have to do is we want to get pxn, and we've got p theta sub n comma xn. So how do we get what we want? We'll just sum again. Sum over all possible values of theta n, p theta n comma xn vector. Okay, so this is called the forward probability summation algorithm. I think it'll look even better on the slides rather than my handwriting. But if you want, I'll just put this part. So you were just asking about this part right here? Okay, so